welcome back. In the lecture on buttons, that was lecture 15, we encountered the pull-up and pull-down resistors. This is an arrangement where in a logic circuit, a large resistor connects a pin from where we obtain a high or low reading to either a logical high source or the ground. If this resistor was connected to a logical high, then we call it a pull-up, and if it was connected to a logical low, we call it a pull-down. This way, when the button is not pressed and its measurement pin is hanging free or floating free, therefore not connected to a high or low pin, then through the pull-up resistor we can essentially assign it with a known value. In lecture 15 we saw this circuit. The measurement pin of the button is connected to both digital pin 2 on the Arduino and via a large 50k ohm resistor to the ground pin of the Arduino. Therefore, this is a pull-down resistor. The large resistor ensures that when the button is not pressed, the yellow jumper wire transmits a low reading to digital pin 2. When the sketch detects this, it can safely assume that the button is not pressed. Keep in mind that we could have just easily had used a pull-up resistor. Connect the resistor to 5 volt and the other pin of the button to ground. You would just modify your sketch so that a high meant that the button was not pressed and a low meant that the button was pressed. The Atmega Microcontroller contains a large, between 20 kΩ and 50 kΩ, depending on the model, pull-up resistor that we can enable so that we can remove the external resistor from our circuit. In the Arduino Duo, the pull-up is between 50 kΩ and 150 kΩ. Let's do that now. So let's modify the original lecture 15 circuit so that the button is connected to the Arduino without the pull-up resistor. We'll use the internal pull-up resistor for that. So let's do the button first. Plug that to pin number 2 on the Arduino, then ground it, ground the other pin of the button, move on to the LED, so it's connected via a small protective resistance to digital pin 13. And finally provide power. Volt rail and ground. Alright, power. And upload sketch. Yep. So, yep. Seems to be working fine. Now, let's have a look at the sketch. So all the preliminary lines are exactly the same as we saw back in lecture 15. The only difference is this line here. So inside the setup function, I'm configuring the button pin, which is pin number 2, and enabling its input pull-up resistor. So just this instruction, pin mode, the number of the pin, and then the constant input pull-up enables the pull-up resistor. And just this allows me to get rid of one resistor from our circuit. Internal pull-up resistors only apply to pins configured as inputs and don't have any effect in the output behavior. Notice how the LED has a protective resistance in series? It would be convenient to be able to replace it with an internal one, but that is technically not a reasonable thing to do. Each LED or other load needs a current limiting resistor appropriate for its characteristics, and it would be too expensive to come up with a way to create a configurable resistance inside the microcontroller. You can have a look at your microcontroller datasheet to find out the exact value of its pull-up resistors, if this is important for your designs. For example, you may want to know how much current will be flowing through the internal pull-up, so you need the exact value of the resistor to do the current calculation. A couple of terms relating to pull-up and pull-down resistors are strong and weak. A strong pull-up or down is a large resistor that only allows a small amount of current to flow through it, while a weak pull-up or down is a smaller resistor that allows more current to flow through it. When you have a choice of a resistor to use for pull-up, you want to choose one that is large enough to not allow too much current to flow through, because otherwise we have a wasted energy. But you also don't want it to be too large, as at some point you will end up with the same problem you had at the very beginning. The voltage, when the button is pressed, will be hard to determine if the current is insufficient to raise a voltage. Large pull-up resistors can also be too slow to respond to quick voltage changes, and in high-speed circuits, like in USB serial communications, this could be a problem. In USB circuits, you will typically find pull-ups in the range of 1 kΩ to 4.7 kΩ. Remember that in our examples of external pull-ups, we typically use resistors between 50 and 60 kΩ. So you can see that the USB pull-up resistors are comparatively very small, so that they can better behave in high-speed communications.